For decades, the high SUV segment in Indonesia has been built on a single foundation, the ladder frame chassis. It is a heavy, rigid skeleton designed for raw durability under extreme load. But that durability has historically required an engineering trade-off. A vehicle built to survive deep mud and jagged rock often struggles on the asphalt. The heavy frame and high center of gravity historically limited steering precision and highway responsiveness. Engineers often call this the ladder frame paradox. You can build a heavy-duty tractor, or you can build a refined passenger vehicle. Finding a way to build both remains a significant mechanical hurdle. The 2024 Toyota Fortuner 2.8 GR Sport 4x4 is a direct response to that exact paradox. Solving it requires an architecture that can take the kinetic impacts of a mountain trail while simultaneously operating as a high-speed, digitally connected node in an urban environment. To achieve this, Toyota moved past simple aesthetic updates, executing a structural restructuring across three primary engineering pillars. First is an increase in thermodynamic output, utilizing the high-displacement 1GD FTV engine block. Second is the management of chassis thermodynamics, replacing standard twin-tube shocks with a specialized monotube suspension architecture. Third is the integration of a digital telematics ecosystem, turning the cabin into a localized broadband hub equipped with active radar safety. By overhauling these three systems, the vehicle is calibrated to perform a wider range of tasks, from low-speed rock crawling to high-speed highway cruising. The physical anchor of this redesign is the powertrain. Toyota shifted from the 2.4-liter paradigm to their flagship 2.8-liter 1GD FTV unit. Looking at this engine cylinder diagram, you see the mechanical alteration responsible for the power jump. The piston stroke elongates from 90.0 to 103.6 millimeters. This downward extension increases the combustion chamber's physical volume. Across 4 cylinders, total engine capacity reaches 2,754.7 cc. This graph maps the resulting torque curve. A longer piston stroke acts like a longer lever on the crankshaft, generating 500 Newton-meters of force from as low as 1,600 RPM. This results in 203.9 horsepower, a 36% increase in power, and a 25% increase in torque compared to the 2.4-liter unit. On the road, this translates to more immediate momentum. The vehicle reaches 100 kilometers per hour in 11.9 seconds. But the more relevant metric for daily use is mid-range acceleration. Pushing from 60 to 80 kilometers per hour now takes 2.8 seconds, nearly a full second faster than the previous 2.4-liter model. This specific acceleration window is a primary indicator of driver confidence during highway overtaking maneuvers. By altering the physical geometry of the cylinders, the 1GD FTV delivers the low-end force required to move a heavy ladder frame, while addressing the sluggish highway response typical of this chassis type. Below the chassis, the GR Sport 4x4 addresses the second half of the paradox through a GR-tuned monotube suspension. Off-road driving introduces a threat known as shock fade. Continuous violent impacts heat the oil inside the suspension. As the oil reaches high temperatures, it loses viscosity, and the shock absorber loses its ability to dampen kinetic energy. This schematic compares 2 suspension architectures. On the left, the traditional twin-tube design uses an inner and outer wall. This dual wall traps heat. Eventually, the fluid boils and gas bubbles form, a process called cavitation. Now look at the right side. The monotube architecture uses a single large cylinder with a floating piston, cleanly separating the suspension oil from high-pressure nitrogen gas. Because the oil sits directly against the outer steel wall of the cylinder, heat transfers immediately into the outside air. The system stays cooler, ensuring the oil maintains its structural integrity. Eliminating the inner tube also creates space for a significantly larger damping piston inside the cylinder. This wider piston increases damping sensitivity. It also provides enough resistive force to eliminate the bottoming out effect, where the rear suspension fully compresses against the stopper when carrying a full payload. This thermal management extends to the wheels. Ventilated disc brakes on all 4 corners are used to disperse heat and prevent brake fade during steep mountain descents. The monotube design uses thermodynamics to ensure the vehicle's handling remains consistent, regardless of the continuous punishment the suspension absorbs. With the mechanical geometry optimized, the final component is the integration of a digital nervous system. This is handled by the second generation of the T-InTouch ecosystem, connecting the vehicle's hardware to the user and a live cellular network. The Fortuner is the first in its class to include an in-car Wi-Fi hotspot. By tapping into a 4G broadband network, the cabin acts as a mobile hub for all passengers. This flowchart shows the security layer of this connectivity, the remote immobilizer. In the event of theft, the owner can send a signal that locks out the engine's ignition sequence. Continuous telemetry runs alongside it, providing exact coordinates through the Find My Car system and geofencing alerts. Inside, this digital integration is housed in a revised cabin featuring leather and suede with GR Sport red stitching. The central interface is a new 9-inch touchscreen head unit. Beyond media, it includes hardware for NFC checking. This feature allows drivers to tap their e-money cards to the dashboard to instantly verify balances, solving a specific friction point at toll gates. Finally, the exterior of the vehicle is monitored by Toyota's Safety Sense 2.0. The pre-collision system uses millimeter wave radar to scan the road ahead. If the system calculates an unavoidable impact, it can trigger autonomous braking. That same radar array powers the dynamic radar cruise control, allowing the vehicle to automatically track the speed of the car ahead and manage following distance on the highway. By layering telematics over a radar array, the Fortuner integrates the vehicle into the owner's digital infrastructure, moving past the analog isolation of traditional off-roaders. The 2024 Fortuner's individual specifications function as a unified system, where digital and mechanical components are designed to cooperate. Downhill Assist Control, or DAC, is a clear example of this synergy. When descending a steep incline, DAC's algorithms measure wheel slip. The computer then fires the mechanical brakes on individual wheels in microbursts, holding the vehicle at a stable 5 km/h crawl without driver input. This schematic demonstrates a crucial companion system, active traction control. If a sensor detects a wheel spinning in the mud, the system clamps the brake on that specific wheel. This forces the mechanical differential to reroute torque to the wheels that still have traction, allowing the vehicle to move forward. This intersection of physics and code is how the ladder frame paradox is dismantled. The geometry of the 1GD FTV engine and the thermal efficiency of the Monotube suspension provide the mechanical brawn, while the T-InTouch network and the TSS radar array supply the intelligent digital brain. It is an execution of the Ever Better Cars philosophy, a platform where durable off-road capability